Okay, so this is an interesting project that we are working on currently, but it's in its infancy, so to say. So the things that we have done so far are pretty much the theoretical point and some implementation done in RTL. So what is the point for this project? So generally, it's based on clocks. It's called UberClock. So you can imagine some great clock. So the clocks can be extracted generally from GPS satellite signals or from MEMS oscillators, quartz crystals, or piezo resonators that are often set in ovens, so to say. Derived from atomic properties. So they differ in a lot of things like absolute accuracy, long-term frequency stability, and so on. So these differences are categorized as clock strata, whereby a clock source must meet a standardized set of requirements for each stratum level. So this work is about achieving and exploiting the properties of a normal multi-mode crystal oscillator that's pretty commercially can be bought, and it's pretty cheap, to achieve a stability comparable to a stratum 2 rubidium clock. That's really expensive and is used when you need a really high precision clock, all at a fraction of the total cost. So we plan on collecting a large empirical data set, constructing empirical prototypes using DSP and numeric methods to mitigate all of the things before I have mentioned, like the temperature variations and other effects. So the project aims for the frequency stability by means of numerous mathematical calculations using open source tools and including HLS flow that we briefly talked about in the Wirecard project. The board that is used here is the board that is by my colleagues, which is a different FPGA board. Maybe I can show it to the camera. So it's an A-Links board as well here that can be seen on the slide, and it's pretty close to the WireGuard board overall. It has 200k LUTs and uses the Arctic 7 FPGA. We also have the AD and DA converters that are plug and play with this board. My colleagues will present that next, so I won't take too long. So what have we done so far is to write the RTL interfaces for the ADC and DAC chips. That's what Nicola and Minala have done, and to test their operations. And we have written some things for the architecture. So overall, I would need to zoom in this definitely. I would need to go through, I don't know if you can zoom it a bit.
I like that, but it's bringing back, so maybe we need to this one.
Okay. So here, generally we would have a DAC and ADC. So this box that's bolded is the FPGA. We have this bad clock, and here we have a resonator physics package. So this physics package is it's a bit abstract for me because this thing is done by an analog engineer, so I'm not an analog engineer. This physics package is available to be seen on GitHub. There's a slide later on here that shows it. So it's the thing that takes the output of the oscillator and scales it, filters it so that we can use it correctly. It's going to be a pretty cheap board. And here, then that goes into the ADC. Later on, this bypass switch is here just so we can debug it better, because if we use this bypass switch, then we bypass the entire path and we can just test out the ADC and the DAC overall. This one is just for high-speed debugging because the input is going at 65 megasamples per second. Here we have these 5 modes or 5 buses. The overall idea is to take the multi-mode oscillator and to use its top 5 modes of oscillation to enhance the overall precision. So then, because these modes are close to each other, we will need to filter them out accordingly and to boost them out as well. So we will need to do a lot of oscillator characterization as well. So here the idea is to take this input and go through a chordic. This chordic would generate a sine wave of a specific frequency. Why do we use this chordic? We use this chordic with the filter. This one is a CIC filter as a down conversion. So because this data is going into the CPU next. We cannot take this data as a 65 megasamples per second. We need to lower it down. So far, we theoretically have established that we are going to use 10 kilohertz for that. Here we have the low-speed debug memory. Generally, we are going to try to use 5 different methods. The first one wouldn't use a CPU at all. You can read here, it says MCU out of the loop. To set channel chordics and gains, let physics package free run. So here is the method 1. We need these gain registers because this downsamples and also attenuates the signal. This later on is upsampled, and the same process is done in reverse. To get back a 65 megahertz per sample into the DAC and later on in the physics package. So here we need the gain stage to be, this is the crux of the entire thing, to modify the DAC data that we get so that it accordingly changes the input to the resonator physics package. So it's like a closed loop, open loop here. Yeah. And here we have a CPU, and the CPU would next take that data and here read raw input samples, compute raw input sample values. Here we have MCU loop with hardware acceleration, servo motor software, and servo motor hardware acceleration. All of the other methods use CPU accordingly, and I won't go into too much detail because we haven't as well gone into too much detail with this. So overall, this would be a general idea. So I'll just go slideshow here. So it's a pretty large picture. This is the analog board that we have so far. And it can be viewed on the GitHub, but this is the photo we have. This is the RTL simulation of the. So this one is the 10 megahertz signal that is down converted. So this is the down converted signal, and that is later on up converted as well. But the attenuation is a bit lower because of the conversion. And for the CPU, we are going to use Litex. The thing is, this is my part that I'm having a bit of a trouble, but I'm going to fix it. These boards look nice and everything is nice, but they aren't that common to see. The ULX3S is more common because it's like a hobby board. Even I think work with this Olimex board is easier than with these ones because not a lot of people have done work on it overall, but we are going to make it work. They are nice boards overall. This is just some Litex, what it does. Many of you are probably familiar with it.